he has done so many different things in so many different fields. But I'd like to summarize his profile by saying that he's across laboratory experiments, seismic processing, hydrology, and many other things. And what is exciting is Thomas, after moving to Memphis in 2019, is also starting his own lab and building a prototype. So he has a very wide range of skills. And so today he'll talk to us about why do earthquakes occur far from the injection wells in California and Oklahoma. So he'll tell us about some induced seismicity, and with no further ado, I will leave you the stage, Thomas.
Beautiful. Good. We could just have everyone go ahead and mute, and then if you have a question during the talk, if Thomas is okay with that, we'll interrupt. Otherwise, wait till the end and use the raise hand feature.
Yes, absolutely. Yeah, thanks. So if you have a question, please feel free to ask during the talk and speak up, because once I go to presenter mode, I won't be able to see you anymore. So I won't be able to see raised hands or anything like that. Okay, are you able to see the slide here, the first slide?
We can see it.
Yes.
Excellent. Okay. Well, yeah, so I just want to say thank you, Marco and Chris and Menandrin, for inviting me. I'm really happy to be able to give the seminar today. I believe Menandrin is in Iceland right now, if I've seen this correctly, so I'm not sure if he's able to join, but certainly thank you for organizing the seminar and inviting me. So we'll be looking into issues related to human-induced seismicity, mainly focusing on sort of geographically on the US, California, Oklahoma, a little bit of Kansas and Texas. And this is really work here that I've been doing in collaboration with a lot of people, as you can see from the names here on this slide. And I also highlighted students who worked on this in yellow and postdoc in orange. And let's jump in. So I thought I will start with giving a little bit of a sort of US perspective, which may be informative. I'm sure you're quite familiar with some aspects of induced seismicity in Europe. And so a little bit sort of introduction to what's been happening and what some recent trends observation in the US, and then we'll look at some mechanisms of induced seismicity, and specifically induced events at large distances and depth from wastewater disposal wells. Okay, let's jump in. So I just put in this slide, in a sense, induced seismicity is sort of almost an unavoidable side effect of some types of subsurface energy production. And here are two examples, one being geothermal, EGS, where the enhancement of permeability is usually associated with some level of induced seismicity, and even during production and injection in geothermal, we oftentimes observe some level of induced seismicity. Similarly, hydraulic fracturing is an operation that pretty much always leads to some level of induced seismicity. So to some extent, the question is more sort of how frequent and what type of magnitude, the size of events that are being induced for these type of operations, and what can we do to mitigate this type of seismic hazard. So this is the induced seismicity side. There's also a positive side effect of doing subsurface operations, which is producing energy. And I thought this is sort of a reasonably interesting observation, that side effect of hydraulic fracturing and the shale gas boom is a reduction in CO2 emissions in the US. So this is taken from the peak in 2006 till about 2019. There was roughly 13% reduction in CO2 emission and really other greenhouse gases. So this is further interesting when compared, for example, to Germany. So this graph is a little bit complicated, but just highlighting the main trend here. If we pick the same time frame, there's about a 10% reduction in CO2 emission in Germany since 2006. And of course, you know, long-term trends are a lot more effective in Germany. I think you can see that because of the switch to more renewable energy. But I think this is simply saying that replacing old coal burning power plants with natural gas has some positive effect on CO2 emissions. And naturally, using renewable and clean energy has also a very positive effect. Okay. All right, so this is the positive stuff. Let's go back to the negative, meaning induced earthquakes. Let's take a look at Oklahoma, which is obviously a very interesting and unexpected place for induced seismicity. So here, the induced events are have mainly been associated with large-scale, almost statewide wastewater disposal operations. So these are extremely high volume of fluids that are re-injected. Commonly, these are produced fluids from oil fields that have very high water cuts, and then they are re-injected into deep geologic formations. Here it's the Arbuckle Formation. So this is just kind of showing a little bit different snapshots in time. So on the left-hand side, I don't know if, I hope you can see my cursor here. There's a picture before 2008, most of the seismicity being focused in the southern part of the state, where we also have a lot of just tectonic faulting and active deformation here. And that picture obviously changed drastically. I think most of us have seen this before, right? So starting in 2011 with the Prague event, this is the white star here. This is the first event that received a lot of attention in the central portion of the state. And then these blue triangles are just the different areas with wastewater disposal that successively light up. So we see that from after 2008, there's a northward migration of the disposal wells, and then also the earthquakes followed in the years 2014 to 2016. So a very nice spatial correlation to where the wastewater disposal is happening and where human-induced earthquakes are occurring. And it's also interesting to see that the 4 magnitude 5 events sort of happen towards the edges of the zone that experienced most of the wastewater disposal. Okay, so you can see Prague here, Fairview, and then Pawnee and the Cushing events in 2016. Okay, and it's also, I think it's really interesting just to point out, Art McGarr and others have shown that in the year 2015, I believe, and then also 2016, the rate of magnitude 3 events in Oklahoma was more than magnitude 3s in California. Okay, and this is interesting now. A more recent time, a lot of the operations shifted to Western Texas, to the Permian Basin. A lot of hydraulic fracturing happening and production from unconventional reservoirs, and this is also associated with wastewater disposal. Here, earthquakes again seem to be related to both hydraulic fracturing and wastewater disposal. But it's just interesting to see at the bottom slide here how the total number of earthquakes really started ramping up pretty rapidly after about 2015. Okay, what is traditionally thought to be the main mechanism is effective stress reduction on pre-stressed faults. And this has been really nicely shown in a controlled injection experiment in the late 60s and 70s. So in Rangeley, Colorado, here I put the title, How to Start and Stop the Earthquake Engine, because the interesting part of this experiment is really that the earthquakes were switched on and off, and by really controlling the larger scale reservoir pressure in Rangeley in northern Colorado. And you can see there's a time series, the vertical bars are the number of earthquakes, and then we have the black line is the reservoir pressure. So if we drop or if we increase and drop the reservoir pressure above or below a critical pressure, they were indeed able to control the seismicity and switch the earthquakes on and off. Now, the interesting observation from this experiment is that the variation in reservoir pressures were fairly high, several MPa variation, and the seismicity was sort of more low level in terms of magnitude. But these absolute numbers are kind of interesting when, in a few slides, when we compare them to other estimates that we think are sufficient to induce earthquakes, let's say in Oklahoma or in states like Kansas. Okay, so here are a few MPa, and we'll compare it to some new calculations here in a little bit. Now, okay, so what are 2 key questions that I would like to discuss today? So First of all, is can we see what is the observational evidence for having indeed distant induced earthquakes? And here, distant meaning we're at several tens of kilometers lateral distance from injection wells. We'll be focusing on wastewater disposal wells here for the most part. But also there is a vertical separation. So a lot of these injection operations are pretty shallow, and we see that earthquakes happen to much larger depth. So there's also a significant distance vertically from injection wells. And then the second question that I'd like to discuss is how are induced stress changes transmitted to large distances. Okay, so obviously a straight buildup of these questions, and then at the very end, just a very brief discussion of potential implications for induced seismic hazard assessment. Okay. So a really nice observation here is from southern Kansas. So a direct continuation of the induced seismicity story in Oklahoma, right? So this is just Oklahoma south here, and we saw the area with basically with a lot of induced earthquakes is just a southward continuation here. But yeah, in Kansas, the observation is almost that there's a bit of a spatial separation of where the wastewater disposal wells, the high rate and high volume disposal wells are located, and where the earthquakes are located. So the top frame shows earthquake locations, bottom frame disposal wells, and the black circles are the same in both areas. So it's indeed interesting to see, right? There's the highest volume injection wells have very few induced earthquakes, and then they happen at larger distances. And we'll come back to this particular study or this particular geographic area in a little bit. But the main point here I just want to make is, well, distances seem to be very large, right? If we just focus in on this patch of really high volume injectors, we have surprisingly large distances to some of these earthquake clusters here. And then, of course, jumping back to Oklahoma, again, another observation of distant induced earthquakes is from the Jones Swarm. Here, the northwest is the Fairview earthquakes. We'll be discussing that also in a little bit. But this is the Jones Swarm area. And here, this is work by Karen et al. In 2014, where they're arguing for these high volume wastewater disposal wells inducing earthquakes at 20 to 30 kilometer distance. And they propose a critical pore pressure change on average of about 0.07 MPa. So this number is obviously interesting, right? I just said before Rangeley it was several MPa. Now we're down to just hundreds or 700ths of an MPa. So very small pressure changes in their model seem to be sufficient to induce earthquakes. And one example I also want to show is from California, a recent study where we looked at potentially, or I almost want to say, likely induced events related to wastewater disposal just west of the San Andreas Fault, actually just west of Parkfield. And this is the San Ardo oil field, actually a very small, compact oil field in Central California, almost kind of halfway between the Bay Area, San Francisco, and Los Angeles. And you can see here, this image is just showing where the wastewater disposal wells are. It's kind of focusing towards the northern part of the oil field, which is the green polygon. And then you have a straight continuation where we see sort of this linear seismicity feature, which is activated sort of at the boundary of where the oil field is and then extending further out north. The largest event in recent history was a magnitude 4.5 in the 1980s here, which is highlighted by the focal mechanism here. We looked at infrared imaging across the area and also constructed a time series and saw sort of a long-term uplift of up to 1 centimeter per year associated with the wastewater disposal. Interestingly, there's a bit of a spatial separation of where the disposal wells are and where the uplift is, which may be related either to heterogeneity and elastic properties, could be just how uplift is resolved due to local topography. There's actually a mountain range and strong topography just to the northeast here of the oil field. But indeed, there's some indication that there's some interaction with elastic deformation and uplift and potential pore-elastic coupling induced by increasing the pore pressure at depth and then resulting in this surface uplift. And we also looked at long-term temporal correlation, see if there is a relation between the injection rates and looking at 1977, which is when the record starts, the publicly available record, until 2020. And we see an overall a pretty strong correlation here, at least if we include seismicity at large distances. So it's not just that one cluster that I was highlighting before that goes out to about 5, 6, 7 kilometers. If we include seismicity out to about 24 kilometers, we get a maximum correlation coefficient of 0.7, 0.71. And here in red is the seismicity rates, are the seismicity rates, and blue again is the injection rate time series. And maybe the most dominant feature is, right, this continuous drop here after, starting in the early 80s, going to early 90s, and then increase again. And the seismicity roughly follows that trend. And then the early 2000s, we have fairly high injection rates and high seismicity. So overall, sort of a reasonably interesting match between what these two time series are showing. And a last point, so these are several steps, right? I should have mentioned that early on, right? A key issue we have in California is that there's just so much natural tectonic seismicity, right? So the overall question is, how can we resolve seismicity sequences or longer term seismicity rate changes that are associated with oil field operation here at wastewater disposal? And so we followed the strategy of looking at INSAR analysis, time series analysis. But here, the last slide I want to show on this particular issue is also the clustering properties specific to the earthquakes are special, or at least distinct from what we see on average in Northern California. So what's this graph showing? Just on the left-hand side, so using a nearest neighbor clustering method, we find the unique parent for each offspring event, and then compute the inter-event time and inter-event distance scaled by main shock magnitude. So basically, this is just a 2D plot showing how close in space and time events are relative to their nearest neighbor. Okay, and if you just focus on the background colors, the reddish colors, and ignore these contours for a minute. So the background shows sort of roughly two statistical modes, which are independent earthquakes that are happening pretty at far distances in space and also are quite separated in time. And then where I wrote aftershocks here, these are the clustered events, right? So naturally, you can see, so there's a log rescale time. So these are events that are happening very close, spatially and temporally. So this is our classic main aftershock cluster. Now, what we see with the St. Ardo seismicity, these bimodal distribution here is a little bit distinct, where we have an additional mode popping up, which is at fairly close distances, comparable to aftershock triggering distances, but at very large times. So this is quite interesting, right? So it could be really indicative of having one geographic area where you have a persistent external forcing that is causing earthquakes to occur. So they're happening in the same area, but they're really spaced out in time. So, sort of indicative for induced seismicity. It could also be indicative for swarm activity, for example, in volcanic areas. So that's still maybe has to be analyzed, but certainly in line with what was suggested previously in geothermal, that induced seismicity can be partially identified by the specific clustering properties here. Okay, that was probably sufficient about the statistics here, but I want to highlight just one interesting observation that has been shown in many different areas in the US, and that is really that geology is very important, the geologic setting. And there is sort of this continuous pattern throughout many of the studies that injection in very high permeability zones right above granitic or metamorphic basement is most problematic in terms of induced seismicity. So this is the same here for St. Ardo. So the in green here is the oil reservoir, where production is focused. Injection is a little bit further to the north, either directly into the fractured upper basement or in the sediments right above. And so there's a really neat article by Rob Skumel in 2018 comparing different areas that show induced seismicity and others that do not have any induced seismicity. And he indeed highlights that the geologic setting may be a key component. And this is, well, I just put this in also study by Horton in SRL in 2012, showing a similar setup where injection is focusing in a high permeability aquifer, and the earthquakes are in the crystalline basement underneath. And this is for the Guy Greenbrier sequence in Arkansas. Okay, so that was, let's just, quite a bit of observation. Let's just maybe summarize real quick what I was trying to show with these slides. So what is the observational evidence for disk-induced earthquakes? We looked at Oklahoma, Kansas, and California, and it looks really that consistently induced earthquakes can occur certainly at distances of more than 20 kilometers, potentially even 50 kilometers, some observations, right, such as in Kansas.
Sorry, Thomas. I think that John has a question.
Oh, yeah, thanks.
Or at least she put on the chat.
Yeah, so in the figure where you had the two seismicity rate and the injection rate in the Ardo well, looks like the seismicity is sort of consistently lagged from the injection rate. Is that the case? And is that indicative, or has that been interpreted in terms of pore pressure migration and where the structures are? Or?
Yeah, that's a really good question. So we do resolve a time lag at the highest correlation here, cross correlation of 14 to 15 months. So it's a bit more than a year. And well, so certainly having a bit of a time lag is indicative of a potential diffusive, pressure diffusion, some process that needs time and not an instantaneous response, right? I mean, that's fair to say. We observe this in Oklahoma and many other areas. And in terms of what it means for the mechanism specifically, I do want to come back to this a little bit. The time lag itself, for me, does not necessarily indicate it's directly related to pressure diffusion, because also the associated prolastic stresses need basically some time to increase in amplitude. However, the reverse, if we do see some instantaneous response, it is sort of an indication that elastic stresses may be more dominant than a slow diffusive process. So it may not answer your question completely, but maybe at the end we can come back and see if we can discuss this in more detail. Sorry about that.
Okay, thanks.
Okay. All right. So more than 20 kilometers, and we highlighted the importance of the above basement injection. And the last point, just to reiterate again, pore pressure seemed to be, well, this is just taken straight from the Karenin 2014 paper, where they hypothesized everything is driven by pore pressure diffusion, right? And then at face value, the required pressure perturbation for failure is much smaller than previously expected, right? At least from, let's say, Rangeley and the Rayleigh paper from the early 70s, okay? All right, so that was the first part, and let's jump into the second part now. Natural question, right? Kind of understanding a little bit mechanistically, what are the processes that are going on? How are these induced stress perturbation transmitted to large distances? What are the main processes? And I would like to suggest 4 different processes that may contribute here. And we'll, maybe we can discuss at the end what the dominant mechanism may be, right? That's probably a large question, but plausibly all four of them, or four of them, I think, have some type of role to play. And so the first one I want to discuss is large-scale pressure diffusion. Let's say it's just a simple layered medium, and pressure is free to diffuse throughout, let's say, a half space, right? Then the second one is introducing flow conduits. So these are specifically, as we'll discuss, fault damage zone, which may act as both lateral but also vertical flow conduits. Poroelastic coupling. So how are changes in the fluid pressure related to changes in the elastic solid in the surrounding volume? And then the last one is event interaction. So this is basically earthquake triggering. Okay, and we'll go through all four of them briefly here, one at a time. So large-scale pressure diffusion brings us back again to the, sorry, this is not the right reference. This is Karen and again, right? Karen study in Science in 2014. And they basically looked at what the pressure perturbation would be for a simple layered model. And the maps are shown in the upper left, and then also the cross section. It's just basically a two-layer model, R buckle, and then the basement underneath. And they run through different values. This is taken here for hydraulic diffusivity of 4 meters squared per second, and this is what we looked at before. They would predict a pressure change of 0.07 MPa at very large distances from the injection walls. So this is one scenario with a very specific hydrogeological structure and some specific values for hydraulic properties, and the resulting pressure perturbation may indeed be quite similar. We think that aftershock triggering stresses magnitudes will be okay. So this. The first one is large-scale pressure diffusion. Then a slight modification to that is to include, as said, flow conduits. So the idea is really here that instead of just having a layered model, we include a fault zone, and specifically a fault damage zone. So let me just show that real quick. So the repeated observation is that the structure of faults are really inducive to having these high permeability pathways just adjacent to high permeability fault cores. And the source of this high permeability is pervasive fracturing and high fracture density, really close to core deformation zones and principal slip zones. And indeed, right, having higher fracture density may help elevate permeability, not just in the lateral sense along strike, but also to larger depth. So working off of that, right, this is a model suggested by Zhang et al., where he includes an isotropic permeability structure for the fault zone with a downward permeability of 10 to the minus 13, and just focus on the upper right-hand panel here, where we see that the fault may indeed, so these contours are different pressure contours due to injection activity, and the fault can really draw down induced pressure perturbation to surprisingly large depth. So this is 4 kilometers beneath the injection zone, and it's about 7 kilometers from the surface. Now, so this is just a model, but there is also some observational evidence that there's some coupling between the fault zones and the vertical migration of seismicity. This is a study by Hornbeck et al. In Nature Communications 2015. This is in Texas now, and he's showing that although the injection is purely focusing in the high permeability Ellenberger dolomite, the seismicity migrates vertically to some extent and reaches depth of almost, or around 7 to 8 kilometers, right? And granted, right, maybe the migration is sort of a bit less systematic than potentially expected from diffusion, but certainly an interesting observation of this linking the shallow injection and then progressively deeper seismicity. Okay, so was the pressure diffusion, purely pressure diffusion story. Now let's look at the coupling between the fluid pressure and the elastic stresses in the solid. And this mechanism has been proposed already, in the 80s by Paul Siegel, related to fluid production-induced seismicity. And the obvious conundrum was, right, how can we create earthquakes if we reduce the reservoir pressure, right? So effectively that should clamp faults shut, and we would actually inhibit a fault slip. And Paul Siegel showed that by overproduction of a reservoir, we actually get pore space collapse, and we get normal faulting towards the edges. So you see sort of extension at the surface, normal faulting towards the edges, but also thrust faulting, and due to compaction here right above the reservoir. And we looked at very much a related case in 2019 work where we looked at groundwater. So the Siegel study was focusing on natural gas production. Here, a similar story, but now for groundwater pumping. And this is overpumping of groundwater in northern Israel, so very close to the Sea of Galilee, just west of the Sea of Galilee. And here the model was just associating the compaction within the aquifer to seismicity just east of it. And in our model, we included a bounding fault, low permeability bounding fault, and the compaction within the reservoir and continuity of stress across this boundary leads to dilation in the just eastward located basin fill. And this is where they also observed a number of normal faulting events just adjacent to the aquifer. So this just sort of summarizing a little bit the idea of how production and pore-elastic coupling can actually lead to induced stress changes and earthquake activity. Now, for the injection case, everything is quite similar, but the signs are reversed now, and you can also see that from the arrows here. So the basic process that's driving deformation is the increase in pore pressure and the elastic expansion of the reservoir. So we have a zone of dilational strain close to the injection well, and then at larger distances we have compressive strains in the radial direction. And this is simply due to the peak displacement not being right, obviously, at the center of the wells, but occurring at some distance, and that sort of switch in the radial displacement away from the peak would lead to a switch in dilational to compressive strains at larger distances. So one interesting aspect, right, from this pore-elastic coupling is that in certain instances, such production case, but also injection case, we do have some indication of the spatial scale and also the magnitude of this process. And this is from observation at the surface, right? I mean, directly, of course, if we have more broader scale reservoir pressures, that's a direct indication. But also looking at uplift for the injection case or subsidence is sort of a direct indication of elastic deformation due to pressure increase in the reservoir, okay? And so this is sort of ties into earlier work by Menno Shirsey, who documented it for Texas. And we also saw this uplift in California, potentially related to pore-elastic reservoir inflation, okay? And this is showing a simple two-dimensional model highlighting that the zone that experiences elastic stresses due to pore-elastic coupling is much larger vertically and laterally than the zone that is just experiencing the direct pressure effects, okay? So left-hand side injection is here in the central layer. This is what the pressure contours would look like. And the right-hand side are the stress contours induced to assuming high pore-elastic coupling within the and high displacement, induced displacement in the injection layer. And we can see both laterally and at depth, we have this larger spatial footprint of the induced stress field. This is showing a cross section at 4 kilometers depth, and highlighting again in blue the area that experienced a direct pressure increase, and then in red separating out what the elastic solid basically experiences in terms of stress changes. And we see a little bit of a transition from in terms of spatial decay, where we're close to the injection well, where it's a bit slower decay, and then at larger distances, this would indicate we see a 1/r³ decay as a function of distance from the injection wells. One last quick thing I want to highlight is also, so for the direct pressure effect, we're obviously not too worried about directional issues and pressure field just being independent of direction. But for resolving the induced stress tensor in the porolastic case, we have to sort of be mindful of superimposing, right, the porolastic stress tensor on top of the tectonic stress field, and that will result in the azimuthal dependence actually of what quadrants experience an increase in stress and what quadrants receive a reduction in the deviatoric stress tensor. Okay, and so both the direction of the tectonic stresses as well as the tectonic faulting regime, right, if we're in compressional or extensional tectonics, will naturally be important for assessing the porolastic stress contributions in more detail. Now, just to show one observation real quick from our porolastic computation, this is now in Fairview. So as I highlighted before, so this is the northwestern part of the state of Oklahoma. And the Fairview earthquakes happen at some distance from a compact source area with a lot of wastewater disposal wells, which conceivably where we expect the highest pore pressure change to occur. And so I highlight here the Fairview cluster, and then at even larger distances, the Woodward cluster. So looking at all of these wells and integrating over the time series, starting in the early 90s and then going to 2016, early 2016, when the Fairview events happened, we can, so these are, again, large distances, right? But again, integrating over the time series, we can estimate roughly what the pore pressure perturbation and the elastic stress field would look like as a function of distance from sort of the center of mass of where the waste water disposal wells are. And so if we compute the extent of direct pore pressure effect and the elastic stresses, we get at larger distances a dominance of elastic stress perturbation. And these indeed seem to be the distances where the Fairview and the Woodward events seem to happen. And in this model, we predict the simple 1/r squared decay, but at depths there may indeed be a more rapid decay as 1/r³. Okay. All right. So the last one. So we went through the pressure diffusion story. Is that potentially porolastic coupling will play a role at large distances. The last one I want to discuss is event-event triggering. So basic, triggering behavior here applied to induced earthquakes. And one of the first studies that I'm aware of was by Sumi et al. And JGR in 2014, who looked at the Prague earthquakes in 2011. So it was actually a series of 3 earthquakes, right? The foreshock being right around magnitude 5, the main shock 5.7, and then an aftershock also close to magnitude 5. So the sequence started here. So event A is the first one, magnitude, the event B was the main shock with magnitude 5.7, and then largest aftershock was about 4.95 at some distances. And in their basic Coulomb stress change computation, they actually make the case that the main shock may have been caused by this foreshock. So sort of this more complex sort of scenario, right, where part of the sequence is directly caused by, let's say, pore pressure change due to injecting fluids, but then this continued cascading of earthquakes is caused by Coulomb stress change, static stress transfer from preceding earthquakes. So, and interestingly, the third event C, was actually in an area of negative Coulomb stress change. So That's just interesting observation. A rather also really neat study, I believe, is from Cochran et al. In 2018, who looked in more detail, now not computing the Coulomb stress changes directly, but looking at the clustering statistics of earthquakes in southern Kansas as a function of distance from injection wells. And they specifically looked at the distribution of inter-event times, and they found that earthquake clusters, and they identified it by waveform cross-correlation and template matching, assembled families, and then looked at the inter-event times of events within the family. So on the left-hand side is a cluster that is more or less typical for near-well occurrences, where we have earthquakes happening over extended periods of time with a fairly Parsonian inter-event time. And then they make the case that at large distances, things look very different, right? So visually, obviously, this is really quite striking, where we have this, what I would, just qualitatively say is a more typical sort of main aftershock sequence, and hence, right, having this short duration earthquake family, a large variability in the inter-event times, but overall short inter-event times is indicative of potential triggering processes that are a lot more dominant at large distances. Okay, so the key takeaway, the interesting observation is here again, right, that jumping back to the map, red is the squares, or where we have most of the wastewater disposal happening, and then these frames here from yellow to purple are the different earthquake families. But the observation is that if we're close to wastewater disposal wells, then the earthquake sequences look more swarm-like, long duration, and Parsonian inter-event times, whereas at large distances, things look more triggered, okay? It does not quite explain how we get to that distance, but at least we know that at large distances, if a fault gets activated, we seem to have fairly efficient triggering processes and potential cascades that may further extend the earthquake sequence, okay? All right, so that was sort of my quick summary of what I believe some of the key processes to be here for for induced earthquake at large distances from injection wells, right? Natural question is, what is the key mechanism, right? Can we just focus on one of them, or what is the one that is most crucial in which situation? And so to make a little bit of progress on that question, we went out to measure fault zone permeability in areas where we believe that permeability is potentially the highest, meaning in geothermal, highly fractured upper basements, areas with a lot of geothermal alterations. And this study here is has just been coming out in GRL. A student from Santa Cruz, Huyun Gu, was the lead author on this study. And so she used a tidal forcing in a number of idle monitoring wells in a geothermal reservoir to estimate fault zone permeability, sort of long-term or time-independent fault zone permeability. And what she found is that there's sort of this consistent threshold, and the one key observation is obviously that the host rock permeability is expected to be much lower than permeability within the fracture zone, within the fault damage zone, I should say. But the other observation is there seems to be this threshold here that even within this highly damaged fractured area, fault zone permeability seems to be capped at around 10 to the minus 13 meters squared, and this is at shallow depth. So this is one sort of piece of the puzzle. Similar observation, we obtained a similar observation for measuring permeability across different core samples, and again, a similar strategy, right? Just try to find an area that's highly fractured. We have a lot of, let's say, geothermal alteration, so we expect that to be indicative of maybe it's the highest end member of what we expect fault zone permeability to be. And this is now for a fault in Japan, but just to really give you the key observation, for me at least, is that again we in the lower right plot, right, you see permeability as a function of depth across the fault, and the highest, using very dense sampling across the fault damage zone, the highest permeability resolve is about 10 to the minus 13, and we have some decrease if we go to larger distances from the core deformation zone. So to sort of synthesize these observations a little bit with the previous study, this is from Rudquist et al. In Geofluids in 2016. He suggests, so this is permeability as a function of depth from a whole suite of different hydraulic stimulation tests, and going both at the left-hand side, kind of the limit for intact rock, and the right-hand side, limit for highly conductive fractures and fault damage zone. And our results are very much in line with what he had, maybe a little bit higher, maybe due to the reasons that I discussed, right? We selected areas where we expect permeability to be almost anomalously high, but at depth of, let's say, the upper 1.5 kilometers, 10 to the minus 13, maybe a sort of a plausible limit, at least what has been limit to what has been determined empirically in terms of long-term permeability. Now, these values become quite interesting, right? If you compare them, for example, to the modeling study by Zhang et al., where he argued for this fluids conduit that will lead to this drawdown and pressure to large depth, right? So they would plot around here, right? The study at around 2.5 kilometers depth. And then also similarly, the study by Karanen et al. In Oklahoma, looking at Arbuckle permeability, would be right around here. So this is sort of just sort of thinking about a little bit what are some empirically, plausibly constrained values for fault zone permeability, and how does it change as a function of depth. And I think this graph obviously nicely highlights the effect of increase in confining pressure, and that perceivably permeability decreases pretty rapidly with depth. Okay, now, and just takeaway point. Okay, long-term permeability, it's probably tough to go beyond 10 to minus 13 at 1.5 kilometer depth. If we go further down, then permeability naturally is expected to be much smaller. Okay, and let me see how we're doing in terms of time. Do we still have 2-3 minutes, or?
Sure, go ahead.
Okay, yeah. So this was part of the discussion a little bit, right? So this is sort of focusing on elastic stress versus pressure diffusion story. And it's basically just saying that, we have to sort of be mindful of what we assume permeability to be in our models, and then if it's also realistic to assume earthquakes to happen at these very large depths and large distances due to simple pressure diffusion mechanism and effective stress reduction, right? So this is sort of the first one, meaning permeability may be quite a bit lower than expected at times. And the second thought is here, contrasting elastic stresses and pressure diffusion, is the timing, right? The timing of when the earthquakes occur. And so naturally, for if we have almost an instantaneous response, it's just a good indication that elastic stresses may play a role. And Paul Siegel has made that point in the 2015 paper. Very interesting work, right, showing that the coupling between what's happening with the fluid pressures and the elastic solid can actually lead to seismicity spikes after injection stops. So this is for one specific faulting regime, so in a normal faulting regime, and also for a specific sort of intermediate distance from the injection well. So here the case is made that the poroelastic coupling actually leads to clamping normal faults at intermediate distances. If we stop injection very abruptly, these clamping stresses are also reduced as instantaneously, but pore pressures may still be fairly or somewhat elevated. So this could lead to the seismicity spike shown in this graph here. And we're arguing for a similar mechanism, but now for reduction in seismicity. And this is really just a different fault orientation, or I should say different faulting regime here. This is in Oklahoma. So here the idea is that the seismicity was not driven by pore pressure, but directly by the elastic stresses. And we're comparing an area with really strong mitigation, right? So we're injecting a lot of fluids, earthquakes appear, largest event magnitude 5, and then injection rates are reduced very rapidly. It's a strong mitigation case. Weak or essentially no mitigation case is, the magnitude 5 happens and we continue injection. And just at phase level, right, I think you can appreciate the difference between the upper panel and the lower panel, where the earthquakes are shut off pretty rapidly in the above case for the strong mitigation, and just continue for, another year when, I guess it continues till the end of the time series here, but just continue with the continuation of injection rates. So long story short, we're saying that for the strong mitigation to be effective at these distances, it's plausible to assume that pore-elastic coupling plays an important role, and these pore-elastic driving stresses were reduced. Here it looks almost instantaneously, but at least very rapidly when injection stopped. Okay, so 2 studies on the importance of timing when the earthquakes happen in terms of untangling the pressure diffusion versus elastic stress story. Okay, so let's wrap up. Last couple of thoughts here. I say pressure diffusion, very important process close to wells and at shallow depth. And then at larger distances, when we have, and also when we have abrupt seismicity changes, it sort of stands to reason that pore-elastic coupling or other forms of elastic stresses may contribute to the induced seismicity sequence. And in terms of seismic hazard implications, right, in the near field, which here I just define as, let's say, roughly within a diffusive length scale. So it depends on the hydraulic properties and the time, the delta T that we observe. That near field will be controlled by the direct pore pressure change. If we go to larger distances and depth, or also for very abrupt changes in operational methods, we see that elastic stresses play a role, and elastic stresses perceivably can extend the spatial reach of injection significantly. So then the hazard, right, that may be sort of an obvious point for the earthquake triggering community, but the hazard is controlled not just by the stress perturbation, but also by the overall volume that's affected. So basically the availability and the number of faults at that particular failure stress. So combining these points 2 and 3, right, and looking at the lower right-hand side, if we're only focusing on pressure diffusion and this, smaller spatial footprint, we would expect sort of a smaller seismic hazard. If we include, let's say, elastic stresses, which decay as 1 over r squared or 1 over r cubed, then we also expect a higher induced seismic hazard. And then maybe that is a little bit out for debate, the last point 4 here, but I'm saying here that the maximum magnitude may then be more controlled by fault size and pre-stress than the operational parameters, right? And so it's just the fault that is, 20 kilometers removed and several kilometers deep, that small stress perturbation that's sort of transmitted due to the induced components is not so the prime driver of what the magnitude of this event will be. Okay. All right. So that's the end. So thank you. Here's some funding agency, and yeah, I'm looking forward to getting some questions and discussing these issues a little bit more. Thank you.
Alex, thanks, Thomas, for this very nice talk. And let's open the stage for questions. I'd like to invite early career scientists to maybe go first, or if they're shy, go later, but go. And please raise your hand and feel free to ask any question.
Marco, I'm happy to start if that's reasonable.
Please go.
Thomas, really nice talk. It's Chris Moran here. I'm not sure if you've seen me, but really nice talk. Really enjoyed that. One thing I was not sure I understand completely was when you talked about event triggering and when you talked about elastic stresses, was just like the separation between static stress changes and dynamic stresses. Because presumably when you're pretty far away from the injection area, the static stress transfer is pretty minor at, I don't know what distances, but I suppose just hear some thoughts of yours on the differences between dynamic stresses and static stresses.
That is a really good point. Yeah. So just a quick disclaimer, right? I have not worked on the events sort of triggering aspect here myself, but just sort of to answer your question sort of off the cuff a little bit, I completely agree, right? So a lot of the directly induced events are very small magnitude. So naturally, let's say static stress perturbation within 1 or 2 rupture dimensions of the magnitude 2s, it's a very small sort of spatial footprint, right? So for the static stress transfer, I guess we would have to make the case of a very efficient cascading process, right? And I'm just kind of putting that out there. I don't know if this is really what's happening, right? But we would kind of make the case for a very efficient cascading process. But if there is indeed the spatial gap, then I agree, right? So the dynamic component of triggering, having some dynamic wave passage, which may be more effective at large distances, would be more plausible then. Yeah, so I think that is a really important point, right? Because in the triggering studies, it's a very big challenge, right? To untangle what is the most dominant mechanism. And it's not entirely different for the induced seismicity case here, right? Although we know a lot more about the anthropogenic components, and we can at least have some ballpark estimate of what the pressures and the stresses will be, there is still a little bit of ambiguity. So I think I'm not giving a clear answer here, but I say it's hard to untangle these mechanisms, and I believe it's correct, right? At these large distances, if it's event interaction would be dynamic stresses, because the static stress field is just very localized for these tiny events.
Right. Right. Yeah, thank you. Thanks a lot. Yeah.
Hey, Jan, please go.
Yeah, so just a question and comment on Chris's question about the